In this lesson, we're going to learn about strategies on solving exponential and logarithmic equations. So, some useful strategies to note. If you're working with exponential equations, one thing that we've already learned is to get the bases of two exponential equations to match and to apply this property that we learned earlier in the class. So that is one very good way of solving exponentials. Another good way is to take a logarithm of both sides of an equation in order to get a variable out of the exponent. This would be a more advanced situation where you aren't able to get the bases to be the same, for instance. And then taking the logarithm of both sides can be helpful. Next, you can rewrite a logarithm equation as an exponential equation using this formula right here, or vice versa. So you could do an exponential equation as a logarithmic equation, and that's another thing you could do if an exponential equation didn't allow you to write the bases the same, for instance. You could combine all logarithms on one side of an equation into a single logarithm and apply this property. The log base b of x equals the log base b of y if and only if x is equal to y. Let's look at some examples, starting with some exponential equations and seeing where each of these different strategies becomes useful. So first off, 3 to the 2x minus 1 equals 27. Well, in this particular case, I know that I can write 27 very easily as a base 3 because 3 to the third power is equal to 27. And if I can do that, that's the easiest thing to apply here. So for instance, the bases are the same, so that tells me that the exponents have to be the same. So I can just continue solving only the exponents. So in this case, I would add 1 to both sides, cancel out the 1, 2x equals 4, and then when I divide both sides by 2, I get x is equal to 2. And that is the solution there. Let's look at another example. 4 to the 5 minus x equals 16 to the 3x minus 1. Again, this is a situation where it's relatively easy to write one base as the other. So for instance, I could leave 4 to the 5x alone. 4 to the 5 minus x alone. Change 16 into 4 squared. And now apply some rules of exponents. So 4 raised to the second power, and then raised to the 3x minus 1. We can multiply 2 times 3x minus 1 and reduce that into 4 to the 6x minus 2. And I have two exponential functions where the base is 4. Likewise, I could have changed both of them into a base 2, but as long as the base is the same, it doesn't matter what the base is. So that means 5 minus x is equal to 6x minus 2, which is a linear equation and relatively easy to solve at this point. So let me come over here where I have a little bit more space. So 5 minus x equals 6x minus 2. So I think what I'll do to start with is add x to both sides. So 5 equals 7x minus 2. And then in getting the exponents on their own, I'm going to add 2 to both sides. So 7 equals 7x. Divide both sides by 7 to cancel this out. 7 over 7 is 1. So the missing value of x is 1. Okay, let's try a different situation. 5 to the 3x is equal to 7. Now, this is not so easy to write 5 in terms of a base 7 or 7 in terms of a base 5. It's not that it's impossible, it's just not straightforward and easy. So there's a couple of strategies that you could do. The first method, so method 1, is you could take the log of both sides. So take log, you could use a common logarithm or a natural logarithm or really a log of any base, but I tend to prefer the natural logarithm. But take a log of both sides. Now, you might be thinking, why on earth would I do that? Logarithms tend to, make situations more complex, so why would I involve a logarithm when it didn't already exist in the first place? The reason is there's an interesting property of logarithms that's going to be helpful with exponential equations. So using method 1, I'm going to take this equation and I'm going to take a natural log of both sides. Now, I'm absolutely able to do that for the exact same reasons that I'm able to add any number that I want to both sides of an equation, subtract any number I want to both sides of an equation. Essentially, these are just functions that are occurring to eat both sides of the equation. I can apply a logarithm to both sides of the equation. As long as I do it to both sides, that will keep things balanced. Now, the interesting thing about this is when I do this, this 3x in the exponent can come out as a multiplier on my logarithm, and therefore I no longer have an exponential equation. So I would have 3x natural log of 5 equals the natural log of 7. Now this is really just a linear equation because natural log of 5 and natural log of 7, these are just simply, they're just representing a number. So the natural log of 5 is just the exponent that you have to raise e to get the value 5. So it's just representing a number, and so essentially this is just a linear equation. To solve this, all I need to do is divide both sides by 3 natural log of 5. So all this stuff cancels out, leaving me with just x. And so I have the natural log of 7 divided by 3 natural log of 5. And in order to solve that, I'm going to need to get the calculator out. So let me bring that up. Okay, so in order to evaluate this, I would need to do the natural log of 7 divided by, in parentheses, 3 natural log 5. I put the denominator in parentheses because I want to make sure the 3 times the natural log of 5 all occurs in the denominator. So order of operations are important here. And that gives us approximately 0.403. And 3 decimals, 4 decimals are generally appropriate here, depending on how your homework asks. Just follow those rules. I'll just stick to 3 decimals in my examples. Okay. But I said there was a second method, so let's explore that. So the second method, I'll just come over here. So method 2. Whoops. The second method is to rewrite the equation as a logarithm rather than as an exponential. So if I have 5 to the 3x power equaling 7. If I want to change this into a logarithm, I would make a logarithm of base 5 of 7 equal to 3x. All right. Next, to solve for x, I would just divide both sides by 3 so that, x is log base 5 of 7 divided by 3. And in order to evaluate log base 5 of 7, you would have to invoke the change of base theorem, which says to take, say, the natural log of the argument divided by the natural log of the original base, which is exactly the same thing as what we got in the previous example. There's not really a faster way. You end up having to do the same sort of steps either way, so it's up to you what you prefer. I tend to prefer using the method 1, taking the log of both sides, but you may find that you prefer method 2, and that's perfectly okay. Either way, you generally do need to approximate your final answer, and if you put this in the calculator, of course, you'll get the same result. All right, let's look at another example. So come on down here. 2 to the x plus 1 is equal to 6. So in this particular example, I'm going to try and mix up the different methods here. So instead of taking the log of both sides, I'm going to switch up and just change it into a logarithmic equation so you can see either way. So this would be a log base 2 of 6 equals the exponent x plus 1. So that means log base 2 of 6 minus 1. So I need to subtract 1 from both sides. What I meant to do equals x. And if you want to approximate that, then you're going to say x equals the natural log of 6 divided by the natural log of 2 minus 1. And then plug that into the calculator. So let me bring that up. So natural log of 6, close parentheses, divided by the natural log of 2, and minus 1. So we get approximately 1.585. All right, and I've got one more example here for this type. Whoops, went too far. There we are. 3 to the 2 minus x equals 5 to the 2x plus 1. Now, this kind is a little bit longer algebraically, but it's really not any more difficult. So what we have to do basically is, in this case, I think I'll take the log of both sides. Oops, that was supposed to be a minus. So 2 minus x equals the natural log, forgetting everything here, natural log of 5 to the 2x plus 1. Now I have two exponents that need to be brought out front. So when I bring the 2 minus x down, it would be 2 minus x times natural log 3. But notice it's the quantity 2 minus x, which is kind of where the lengthy algebra is going to come in. Again, over here, same thing. I have the quantity 2x plus 1 times the natural log of 5. Now, at this point, it really is a linear equation, and so you're just solving a basic linear equation. It just looks more complex because the logarithm's involved. But basically what I need to do is I need to take, say, the natural log of 3, distribute it into this set of parentheses. So 2 natural log 3 minus x natural log 3. And same thing on the other side. Just take the natural log 5 and distribute it into these parentheses. So 2x natural log 5 plus natural log 5. Now, the next step that I need to do is get everything that has the variable x on one side of the equation and everything that's just a constant on the other side of the equation. So I will say subtract natural log 5 over this way and add x natural log 3 the other way. So those are going to cancel. The negative x natural log 3 and the positive x natural log 3 are going to cancel. So when I combine these, I'm going to end up with this. I'm going to need a little bit more space, it looks like. So 2 natural log 3 minus natural log 5. I can't combine those because they're not like terms. Similarly, on the other side, 2x natural log 5 plus x natural log 3. I can't combine any of those because they're not like terms either. But on the right-hand side, each of these have a factor of x, which I could use the distributive property and factor that out. Okay, so I still have this stuff on the left-hand side. Now, to solve for x, all I need to do is divide by this constant right here, the 2 natural log 5 plus the natural log of 3. And I'm going to divide both sides by that. So that means x is equal to 2 natural log 3 minus natural log 5 divided by 2 natural log 5 plus the natural log of 3. Algebraically, that wasn't, a short process, but it really wasn't a difficult process, because in the end, it's really all just solving linear equations. In order to approximate the answer, we have to kind of be careful with the parentheses here. So 2 natural log 3 minus natural log 5. So I have a set of parentheses just for the numerator, then divided by the denominator, which is 2 natural log 5 plus natural log 3. And I have a set of parentheses just for the denominator as well. So that gives me approximately 0.136. And that's as bad as those will get. It's lengthy, but still, it's not a difficult process once you practice it a couple of times. A couple more examples, just to make sure we know we're adequately prepared for the homework. All right, this one looks a little bit different because I have e involved. And students tend to think e makes things more difficult, but it really doesn't. It's just a number, 2.71828. It goes on forever, but it's just a number, so you just work with these, same as any equation. So one thing you could do, for instance, if you chose to rewrite this as a logarithmic equation, you could say, all right, log base e of 12 is equal to that exponent 4x. But the nice thing about this is log base e, we know, is the natural log. We could have actually really gone straight to this step, knowing that log base e results in the natural log. Then the next thing that we do is just divide both sides by 4. So x is equal to the natural log of 12 divided by 4, which, if I get the calculator out, I can approximate. So it would be the natural log of 12 divided by 4. So 0.621. Okay, I'm going to do another one here. 0.04 times the 13.2 raised to the x power equals 32. All right, so before I can do any work in changing this into a logarithm, the first thing that I need to do is get it so that there's no multiplying constant of 0.04. And that's simple enough to do just by dividing both sides by 0.04. So that will cancel it out over here. Then I have 13.2 to the x, and 32 divided by 0.04. I'll just grab the calculator and see what that is. So 32 divided by 0.04, 800. Okay, now to solve this, since it's just a simple exponential, I think I'll just switch it into logarithmic form. So it would be a log base 13.2 of 800 is equal to that exponent of x. So all I need to do then is just approximate what that would be on the calculator. And remember, you can do this as natural log of 800 divided by the natural log of 13.2 just through the change of base theorem. So 2.591. And I have one last example for exponentials. Then we're going to move on to logarithmics. Okay, so 5 times 4 raised to the 2 minus x minus 7 equals 28. In this situation, I can't really start changing things into logarithms until I get these added, multiplied, all these constants out of the problem. So the first thing I'm going to do is add 7 to both sides. So that cancels the constant minus 7 out. So 5 times 4 to the 2 minus x equals 35. Next, I have this constant multiplier of 5, and I can get rid of it if I just divide both sides by the constant. So 4 to the 2 minus x equals 7. Now, what I need to do next is either take the log of both sides or change it into a logarithmic equation, whichever you prefer. So I'll change it into a logarithmic equation because the resulting logarithm would be fairly simple to work with. Log base 4 of 7 equals 2 minus x. And that means if I subtract 2 from both sides, probably going to need to get more space here, then I have log base 4 of 7 minus 2 equals negative x. But then I have to divide everything through by negative 1. And when you do that, so it's going to, the negative is going to make, when I apply the negative, it's going to make this term negative and this term positive. Essentially, it just turns around that binomial. So it becomes 2 minus log base 4 of 7. Now, I could write this as 2 minus natural log of 7 divided by natural log of 4 if I wanted to express it that way before I put it into the calculator. But if you know the change of base formula well enough, you can just plug it directly in, and that's completely fine. 2 minus natural log of 7 divided by natural log of 4, we get 0.596. Now we're going to talk about some logarithmic equations. In the case that no constant exists in an equation involving logarithms, and all logarithms are of the same base, the best strategy is to combine all logarithms into a single logarithm on each side of the equation, and use this property below to drop the logarithms on both sides and continue solving only the arguments of the logarithms. One thing to keep in mind is that the domain of a logarithmic function is 0 to infinity. So answers that lead to a negative value or 0 on the argument of the logarithm have to be discarded. So let's look at some examples. Starting with log base 7 of x plus log base 7 of the quantity x minus 2 equals log base 7 of the quantity x plus 4. So all three of these terms involve a log of the same base. There's no constants that are floating around. I don't have, say, like plus 6 over here. That would be a constant floating. So I don't have that. which means the best strategy is going to combine all logarithms on each side. So on the left-hand side, I can combine these two logarithms. When you have two logarithms that are added, you combine them into one logarithm where the arguments are multiplied. So using one of those properties that we learned earlier in the class about logarithms. Once you have two logarithms of the same base equal to one another on each side of an equation, you're free to drop the logarithms at that point. Similarly, the way that we go about solving exponential functions, where we get the base of the exponential functions the same on each side, we can basically drop the base and continue solving only the exponents. It's the exact same principle. So this would mean that I could take the next step to be x times x minus 2, set that equal to x plus 4, and continue solving this, and not worry about logarithms anymore. Essentially, there's more going on here than that. You are essentially taking both sides of the equation, making it an exponent where the base is 7, using different properties of logarithms to simplify. You don't really see any of that in solving these. It's okay. Once you get both logarithms of the same base equal to one another, you can drop the logarithms. All right, so then this becomes x squared minus 2x equals x plus 4. Since there's a square in the problem, I need to bring everything to one side, get it set equal to 0, prepare to factor, and so forth. So x squared, if I subtract x over, it's going to be minus 3x when I combine. And I need to subtract the 4 over, so it's going to be a minus 4 here. Which means when this gets factored, I have 4 and 1 here, minus 4 plus 1, so that x is equal to 4 and x is equal to negative 1. Now, these two are potential solutions at this point. They're not necessarily solutions to the problem. The reason they're potential solutions is because when it comes to the original equation, I can't have any value being a solution that leads to the argument of a logarithm being negative. So for instance, when I plug in x equals 4, I get log base 7 of 4 plus log base 7 of 4 minus 2, which is 2, equals log base 7 of 8. The arguments, so the 4, the 2, and the 8, these are all positive numbers, and that's fine, as long as they're positive numbers. When I use x equals negative 1, well, this first term becomes log base 7 of negative 1 plus log base 7 of negative 3 equals log base 7 of 3. Now, it's perfectly okay on this hand because the 3 is positive. But the issue is right here and also right here. I have negative values in the arguments of my logarithms. And because of that, x equals negative 1 is not an actual solution to the problem. It's called an extraneous solution. It's introduced through the process of solving, which occurs sometimes when you have restricted domain functions that have restricted domains. So what I need to do is any number that's going to lead to the argument of even just one logarithm being negative, I have to throw it out. So I just come back down to my solutions, and that right there is perfectly fine to indicate to your instructor on a test that you found that solution, but you're throwing it out. In the homework, sometimes they'll just ask you to answer with the actual solutions. So in this case, you would just answer with 4. Sometimes they ask you to answer the solutions and the extraneous solutions so that you show that you're knowing what each one is. All right, let's look at another example. Oh, I'm sorry, I have one more thing about this one before I move forward. One of the most common pitfalls that students run into is dropping the logarithms before combining them. So like for instance, in this particular problem, like I've seen students, I'm going to do this in red because it's wrong. I've seen students just drop the logarithms. They see that all the logarithms are of the same base, and they just drop them and say x plus x minus 2 equals x plus 4. And then they work the problem out and they get some answer for x. It just doesn't work that way. You can't work the problem through that way. I wish you could. It would actually be a whole lot easier, but it just doesn't work. You have to use those properties of logarithms. And those properties of logarithms tell us that we have to combine all logarithms into a single logarithm first, and then drop the logarithms. So the next example. The natural log of 4x plus 3 minus the natural log of x plus 2 equals the natural log of 3. Okay, in this example, I have two logarithms that are of the same base and they're subtracted. I can combine them into a single logarithm by dividing their arguments. Once I do that, I now have two logarithms of the same base, and I can drop those logarithms. So this tells me that 4 times x plus 3 divided by x plus 2 is equal to the quantity 3. The next step that I need to do is multiply both sides by the denominator x plus 2. So 4x plus 3 equals 3x plus 6. I went ahead and multiplied the 3 into those parentheses. And this is a linear equation, so I just need to get x by itself. So I'll subtract 3x from both sides. That's going to cancel that out. And then I'll subtract 3 from both sides. That's going to cancel that out. So 4x minus 3x is x. 6 minus 3 is 3. And I still do need to check to make sure that the value given here does not lead to any negative arguments of logarithms, and it certainly doesn't, because for the first one, 4 times 3 is 12, plus an additional 3 is 15. It's positive. That's fine. 3 plus 2 is 5. That's positive. It's fine. So this is an actual solution. One thing that you'll kind of start noticing is that negatives tend to get thrown out, positives tend to not get thrown out. But don't get caught up in that. That's not the test. Most of the time negatives get thrown out, and most of the time positives stay. But there are situations where the negatives get thrown out. There are times where you get two positives and they both get thrown out. So you just have to test, and it's a very easy test, so it's not necessarily going to take you any more time to perform that test. Now, there's another type of logarithmic equation you'll run into, and that's when a constant exists in the equation. And when a constant exists in the equation, the best strategy is to combine all logarithms into a single logarithm on one side of the equation, set equal to that constant. Then rewrite the equation as an exponential and continue solving the exponential. So, for instance, log base 4 of the quantity 2x plus 54 equals 3. It's already a logarithm of a base of an argument equal to 3. It's already one logarithm equal to a constant. So I don't need to use rules of logarithms to do anything with that. What I do need to do, however, because there's a variable in the argument of the logarithm, I'm going to have to change it to exponential form to solve it. So my base is 4. the exponent is 3, and it's equal to 2x plus 54. So I'm just using that rule of how to change exponential form into logarithmic form. Now, 4 to the third power is 64. So I'll write that. And what I need to do next is subtract 54 from both sides. I'll bring this up a little bit. So I get 10 equals 2x. And then I'm going to divide both sides by 2 so that x is equal to 5. And 5 does not lead to a negative number on the argument of that logarithm, so I'm all done. Right, here's another example. Log base 2 of x plus 5 plus log base 2 of x plus 3 equals 3. Okay, so I'm going to first combine those logarithms into a single logarithm. So I'm going to make this log base 2 of x plus 5 times x plus 3 equals 3. Because I can't change it into exponential form until that happens. I have to just have a single logarithm equal to a constant. All right, now I take the base of my logarithm, which is 2, raise it to the third power, and set that equal to x plus 5 times x plus 3. Now I no longer have logarithms involved. Once I take 2 to the third power, that's just a constant, which is 8. I no longer have exponential equations anymore. This is really just a quadratic. I need to FOIL the x plus 5 times the x plus 3. So it would be x squared plus 3x plus 5x plus 15. And I need to get like terms combined, everything to one side of the equation. So I'm going to subtract the 8 over, and I'm going to combine the 3x and the 5x. So 3x plus 5x gives me 8x, and I am subtracting the 8 over, so 15 minus 8 would be 7. So I have x squared plus x plus 7. Now, to solve this, I need to factor. So let's see how this factors. Looks like if I'm using 7 and 1, it should work out just fine. So that tells me my potential solutions here are x equals negative 7 and x equals negative 1. So you might be thinking, if you take that knee-jerk reaction of to just eliminate all of the negative solutions, well, that will be a problem here, because if you put negative 7 in, then in the first set of parentheses, negative 7 plus 5 is negative 2. That right there, that's an issue. So we have to throw out negative 7 as a solution. It's an extraneous solution. All right, but if I put x equals negative 1 into this first parentheses, negative 1 plus 5 is positive 4. That's okay. Negative 1 plus 3 is positive 2. That's also okay. So negative 1 is a valid solution here. So you can have negative answers. You just have to test each one and see if, what the test tells you. All right, one last example here. Let me, too far there. Perfect. Log base 4 of the quantity x plus 3 minus 1 is equal to log base 4 of the quantity 2 minus x. All right, so in order to do this process, I have to have all logarithms combined on one single logarithm on one side of the equation, the constant on the other. I'm doing this because of that constant 1. So what I can do is I can add 1 to both sides. That's perfectly permissible. So I would have log base 4 of x plus 3 equals log base 4 2 minus x plus 1. So I've just moved the 1 to the other side. Next, I'm going to move the logarithm, so log base 4 of 2 minus x, I'm going to move it over. And that's perfectly okay to do. You just subtract that entire term. So this minus that cancels out completely and gives me log base 4 of x plus 3 minus log base 4 of 2 minus x equals positive 1. All right, next thing that I need to do is combine these two logarithms into a single logarithm. Since they are subtracted, that means I'm going to divide their arguments, and that's what I end up with when I divide. And now I have a single logarithm equal to a constant. I can change this into an exponential equation by taking the base raised to the first power in this case equal to that argument. All right, 4 to the first power is of course just 4, so that's nice. What I would need to do is multiply both sides of the equation by the quantity 2 minus x. So I get 4 times 2 minus x on the left-hand side. The 2 minus x's cancel out on the right, so that's just x plus 3. So I have 8 minus 4x equals x plus 3. And if I add 4x to both sides, subtract 3 from both sides, so the 3's are going to cancel, these are going to cancel. 8 minus 3 is 5. 4x plus x is 5x. I'm almost done. I just need to divide both sides by 5 so that x is equal to 1. And it's a positive number, but I still can't say for sure that it's a valid solution until I go and plug it into the original arguments just to make sure it works out. So way up here. All right, so in the argument of the first logarithm, 1 plus 3 would give me 4. That's a positive number, no problem. In the next one, it would be 2 minus 1, which would be positive 1, which is also just fine. So x equals 1 is a valid solution.